Okay, so this video is going to talk about Gaussian elimination, back substitution, and Gauss-Jordan elimination. Let's get into it. So to solve a system of linear equations efficiently, the end goal is to be able to use Gauss-Jordan fluently, as it is just a merge between Gaussian elimination and back substitution. So let's get to know Gaussian elimination. All it is reducing a matrix into row echelon form. Now what echelon means, it's actually a signal in crowd control, where the squad gets into a diagonal form. And that's exactly what happens in REF. So all numbers of each row are to the right of the first non-zero digit in the above row. So this is the first non-zero digit, and the row below it, the digit is to the right of it. So this is in REF. Same goes here and here. Now you're thinking, okay, this is a bit strange. There's a row of zeros. There's nothing to the right of the first non-zero digit in the above row. But it still counts because it's not violating any rules. It's pretty calm. But if this row moves itself up the scale, then this row here has nothing to be to the right of, so it's no longer in row echelon form. So you may need to perform some row operations and get this out of the way. And this one isn't in row echelon form because it's not to the right of anything. Same with this one, and yeah, this row of zeros is the exact same as this case here. So let's do an example. You get given a system of linear equations and they want you to solve it. First thing you want to do is put it into an augmented matrix, but because this is a homogeneous system of linear equations, you don't actually need to do that, because any row operations that you perform here on the zeros is just going to give you back 0. So in row echelon form, to put something in row echelon form, there's a specific technique where you use a pivot point and you reduce every digit below it, all the numbers in the column all these numbers here below it, to 0. Don't worry about what happens over here if you start getting interesting fractions. Usually it will sort itself out. And yep, that's what you should get next. There's a row of zeros below, and yeah, it doesn't matter what happens over here. Now you move on to the next pivot point. And the reason why it's called a pivot point is because you're sort of spinning down like this all the way until you get all the numbers below the point that you're pivoting to 0. So eventually you'll reach the end. This is your last pivot point. And this is in row echelon form, and this is Gaussian elimination. And all back substitution is putting the row echelon form matrix back into equation form, and then what you're doing is you're substituting your values back into the equation above it until you get a solution. And now if you don't really write your solutions like this as a solution set, especially in linear algebra, because you start getting lots of solutions, you start getting equations as solutions, it's much easier to do it this way than to individually write it out, although both forms are correct. So in Gauss-Jordan elimination, we don't have to convert the matrix back into equation form to solve like we did here. We don't do this. We actually do this in the matrix itself. So, however, we take one step further when we do Gauss-Jordan, because we don't just leave it here. We put something into reduced row echelon form instead of back substituting. So you'll get a matrix that looks like this when it's in reduced row echelon form. And if you're working with slightly larger matrices, the same rule follows. There is just a diagonal one down the middle. And a word of wisdom for those who are just being introduced to this topic, it does get a little bit hectic, and sometimes you can't be bothered to carry the equation or to carry the method all the way through to row reduced echelon form, and you might feel like it's easier to revert back to back substitution. Don't do that. That's not Gauss-Jordan elimination. It gets easier. Just follow through with it. Onwards. So let's do an example. Now you're given a slightly more interesting set of system of linear equations. Now let's use Gauss-Jordan elimination to solve it. So this one, it actually does need an augmented matrix because the row operations that you perform here will change your answers. And this one, I'm actually going to let you guys do it because all it is using row operations. And let's see if you can figure it out. The answer is this. And yeah, put it in this set and pause the video and give it a go. Alright, this is how I did it. So the main two things to note is, yes, use your pivot point, reduce everything below it to 0. Sometimes you may see that, okay, there's a 1, 1 here, and I can actually knock those two out, which can speed up the process. Instead of reducing 0, 0, 1 here, you can just knock that straight out there, which makes it a lot quicker. Another thing to note, yes, I made a mistake. You will make mistakes doing these things. It's okay. With more practice, you will minimize them. If you see that, I think that's pretty much it. It's pretty straightforward. Alright, so you have learnt how to do Gaussian elimination, how to put something in row echelon form, how to identify when something is not in row echelon form, which is very important. You've learnt how to do an example. You've learnt how to use back substitution, and because you all know all of that, you now know Gauss-Jordan elimination. And now you can solve any system of linear equation, because this is as far as it goes. Thanks for watching, guys.